Environmental Exposure and Fetal Origins. I'm David Slusky from the University of Kansas. This session is being live streamed all around the world, so if you are not physically here with us in Boston and you want to ask a question later, you can tweet at me at David Slusky, S-L-U-S-K-Y, no T, and I will do my best to ask your question on your behalf. Our first presentation is from Richard DeSalvo from Rochester.
There we go. All right, so I'm going to present this joint work with Elaine on drinking water contamination and infant health outcomes. And so research question is, what are the effects of tap water contamination on low birth weight and preterm birth? And we're studying Pennsylvania over this time period. This is an important question because, I think, because babies are important and drinking water is important. So what we do is we take two steps. First step, we replicate this paper that has already studied this question by Janet Carey and her colleagues, and we add a few sensitivity checks. And the second step is we extend the paper using a different and probably better measure of drinking water contamination. So to illustrate sort of the identification strategy that's behind their paper, the CZM&S paper and our paper, I'll just start with, these are the Pennsylvania public water systems. So we have the shape file that probably a lot of people know, some people know about. Pennsylvania is kind of a unique state, and then it has this information. And so these are the public water systems that have a nitrate MCL violation. And maybe you can see them, they're in red. It's pretty rare to have a MCL violation. This basically means that you have too much contamination in the water, and so then the Safe Drinking Water Act puts the public water system in a state of violation. So if we just focus on this little sort of long public water system to the west of Philadelphia, this is what MCL violation data looks like. So it's basically intervals of time in which you're in violation and you're not within violation. So the blue bars are nitrate MCL violations. And the identification strategy is a within mother design. So pretend these two blocks are gestation periods for mothers, and let's say these are from the same mother, so they're siblings. The red block intersects an MCL, the green block doesn't. We would consider the red block to be treated, green block not to be treated with drinking water contamination, and the within mother design compares these two if they have the same mother. So in our extension, we extend the analysis to drinking water samples. So these are the samples for the same system. There's a lot of nitrate samples for this system, so it seems to have had a problem with nitrate. The MCL for nitrate's 10, so you can kind of see that this system has a lot of nitrate in the water. And what we do here is we simply find the intersection between the samples, the gestation periods, take an average, and that gives us sort of an average level of contamination in the water faced by the birth. And this is a point where I'd be interested in any input. Basically, we have, at this point, roughly 90 different drinking water contaminants. So I'm not going to run 90 regressions, and you'll see later that even when I split by, say, like 12 regressions, the results don't look very stable. So I really want to aggregate things somehow, and the approach we take to aggregation is really not super great, I don't think. So for instance, we want to create nitrates category, so we want to aggregate nitrate and nitrite. It's arguable whether we should do this because nitrite's a lot worse than nitrate in terms of the medical literature. But anyway, what we do is we define a result relative to MCL. So basically if we see average result. Okay. Didn't like this. I really don't like this approach. Okay, fine. Yeah. So anyway, we take the ratio relative to MCL, and we get this result relative to MCL measure, and our hope is that that means something. Doesn't have any units at this point. And then we take an average across contaminants we equally weight contaminants, which is also another point of contention, whether we should be doing that. And that gives us sort of this measure, which has no meaning, but except that when it's bigger, there's more contamination. And then because that measure is super right skewed and a really ugly measure, we then standardize that measure, giving it even less meaning. So any input on how to aggregate contamination would be interesting, useful. So we have this within mother design. I didn't show the regression specification because I think it's kind of straightforward, except we have these ton of control variables, and this is really following the CZMNS paper. And there are lots of control variables, and they actually matter for the inference quite a bit. So take that as you will. So because we're replicating this paper in big part of our work, I think it's really good to compare with what our data looks like compared to theirs. So we have a different state and a different time period. And what's interesting is that we have more births, like 50% more births, because we have Pennsylvania, we have a bigger state, and we have another year of data relative to them. But we actually have fewer births exposed to an MCL violation. So actually, we're about half as many births exposed to an MCL violation. So we have actually probably less statistical power to detect effects of MCL violations, but we kind of make up for that by the fact that we have pretty much full coverage of births with at least some drinking water quality sample measure. Another interesting difference between us and what they find in New Jersey is that it looks like MCL violations are related to higher SES status in our data, which never happens, right? Because pollution always seems to be related to SES negatively. But anyway, so if you look at our data, the MCL exposed births are basically less likely to be from black mothers, and actually in the raw data, they have lower birth, or better birth outcomes on low birth weight and preterm birth. It's also interesting that they move more. So we get opposite results here as well. All these differences are statistically significant because these are just means, and we have 700,000 data points, so standard errors are very small on these things. So if you look at the sampling data and you sort of cut it by asking, basically you cut the sampling data and do kind of the same exercise, you return to the, low SES means more contamination story, which is kind of interesting that you get different results depending on the measure. So these are the results for black and mobility, and then get the same pattern as I said. So here are the regression results. So CZMNS doesn't find any effect on mobility, and we find an effect on mobility. So basically, when there is drinking water contamination, mothers do seem to switch in our data, and the effect size is almost 3 times the size. So we find different results there. And of course, this is kind of a funny picture, I think. So of course, they find effects on low birth weight, and we just don't find effects on low birth weight, although the point estimates are almost the same. So I think I take this as basically we're finding the same results, although if we wrote it up, we'd say this was a 0, because I guess that's the standard. And we also find kind of inferences reversed for preterm birth, but actually our point estimate's very different here, although the standard errors are huge in MCL regressions. Basically the standard errors are always large with these types of violation regressions. Anyway, so compared to the previous plots, we have some additional controls. The main one is plurality, twin births, triplets, etc. And I think that was included in CZMNS, at least they never mention it. And when we include it, it actually changes our inference quite a bit. Low birth weight coefficient changes quite a bit, and the preterm birth coefficient changes enough to make it so that we would say that there was nothing, when in fact, actually, the point estimate's still bigger here. And if we actually remove plural births, it's a different way to control for them rather than putting in dummies for twins and stuff. We actually, not much changes, except we can now say that preterm birth is affected by it. But anyway, I just want to say that we're almost getting the same results in the replication, except that depending on what controls you do, what you infer according to the cutoff of 5% will change. So for the extension, it's a lot nicer because we have a lot more data, so the standard errors are much smaller. And we generally find, if we break it up by all bacterial chemical contaminants, that chemical contaminants seem to be more important than bacterial contaminants. In fact, the bacterial one is only significant at the 10% level in terms of its effect on low birth weight and preterm birth. But the standard errors are very small. These are quite precisely estimated effects when you use sampling data. And If we split it by trimester, I think this is an interesting result, but I kind of want to dig into it further before I put too much weight on it. It seems like everything is in the third trimester. That's kind of very stark for me, and I was very surprised that that was what we found. And then here's the big selling point of the paper, which wasn't successful, but this was kind of the goal going into it, is that with sampling data, we have contaminants, a lot of contaminant groups, and we have a lot of data on each contaminant group. So obviously what you'd want to do is say, does this contaminant affect low birth weight versus that? And what's very interesting is that if we group contaminants into the all category or the chemical category or the bacterial categories, which are kind of like to partition the set of contaminants, there's a lot of data there, and we get deleterious effects. But when we start splitting out by contaminant groups, it's really a wash. Like, we get a lot of negative, probably more negative coefficients than positive ones. So I guess maybe this method just isn't a good method for trying to inform the regulation debate. Thank you. So we run this quick back of the envelope effect simulation because, as I said, the units they're standardized, there are MCLs, they don't really make any sense. So what we do is we run a quick simulation where we imagine that we take all the births that have above median contamination and then bring them to the median level of contamination. I think that's interpretable, right? It's like this huge investment in public drinking water quality where we sort of collapse the distribution. And what we find is, if you look at the chemical one, which is the biggest number, so let's focus on that, is we find that there's a 0.17 percentage point decline in low birth weight propensity in Pennsylvania, which is a reasonable magnitude from a 6.5% rate. So the upshot is that if we did invest really heavily in drinking water contamination, we would see some effect, discernible effect. And we can do the same thing for preterm birth. It's very similar because the estimates aren't actually in practice very different. And then finally, just to wrap up, just want to compare some results. I put Michelle's results at the bottom because I'm discussing her paper. So anyway, I think a reasonable, this variable is very right skewed, so I think perhaps a reasonable change would be from the 25th to the 75th percentile. I mean, if I use standard deviations, I'll get a giant number because standard deviation's actually a big thing in some sense. But anyway, if you use the interquartile range change, basically, you see that the estimates from our sampling results are actually quite similar to the estimate from the MCLs. They all kind of cluster together. Of course, they're statistically indistinguishable because the MCL regressions, all of these kind of have confidence intervals that go from 0 to 0.6, so they kind of span almost the whole x-axis. So obviously they're not statistically different, but the point estimates cluster together as well. So I think we're kind of using different measures for finding the same general relationship between drinking water contamination and birth outcomes. Oh yeah. The red one is positive, the blue one is negative, or the green one, I guess. And that's because positive effects on low birth weight are bad. So I make it red, even though it confuses me too. But I compare it with some of the other literature. So the easy pass estimate is, basically easy pass comes in and that's the effect on low birth weight from changing a toll booth to easy pass, which I think is huge. And if you put it in context of other things, it's a huge number. And then, of course, food stamps and WIC. And then TRI facility opening is another air pollution measure and another air pollution study. And then we'll see more about lusts in a bit. So these are my findings. And that's what I have. Thank you.
Our discussant for this is Dan Grossman from West Virginia University.
All right, thanks. I really enjoyed the paper. Thanks for giving me the chance to discuss it. They're investigating the relationship between drinking water contamination and infant health in Pennsylvania. As you'll see in a few minutes, I really like this topic, and I think it's a really important topic to look into. using variation in whether a local water source had violations, as well as the actual readings from local testing, which I think is the really, really cool selling point of this. The actual readings is a really nice thing. Just because, going for, basically the violations just give you the chance to, a binary from 0 to 1, but, it's based on some cutoff. Giving the actual readings really gives you a chance to really explore whether or not there was a big change in the contaminant, or whether or not it was just, going from, whatever, 14.9 to 15, and all of a sudden you're in violation. So I think that's a really important level of variation that you have in your data. So I'll skip through the overview because I have a bunch of things here. So I really think this is a really interesting study, and the way that in the write-up, I think it'd be really good to stress what you have in your study that's that's over and above what previous work has done. So it's obviously really important to compare it to the previous work, but more kind of push more on the fact that this continuous testing data is really a strength. And a little bit more discussion of what the IV that you actually use in the paper would be nice. So the other thing I was thinking, and you'll see in my paper as well, what about fertility? So if violations are really affecting in utero, mothers in utero, you might expect fertility rates to drop. I assume that you could probably get population levels at the district level, at the water district level. They might be a little bit imprecise, but I think that would be an interesting outcome in its own right. So the measures, I wasn't exactly sure. You talk about a daily measure of these contaminants, and I wasn't sure what happens. Clearly you're not getting contaminant per day measures, so I wasn't sure what happens when, a contaminant is only measured once over, a month or a 9-month period or whatever, and how that kind of gets put into your measures. So I'm going to speak out of both sides of my mouth now. I really do like the contaminants by group analysis, but as you mentioned in your own presentation, it's sort of treating each contaminant equally, or equally based on whatever the MCL level is. So in some ways, I think the Harding paper that you cite looks at just focuses on contaminants that are linked to specific defects. So that might be a good way to sort of target your analysis to kind of focus on the defects that the birth outcomes that you would expect based on these contaminants. So this is kind of far removed from the EPA standards. The EPA is only really interested in whether or not you're above a specific MCL. But in some sense, what you're doing is really interesting, because maybe that's not the right way we should be thinking about it, and maybe the EPA should be more worried about total contaminant level, and not just whether or not you're over an MCL for a specific contaminant. So in the end, I think I really liked that analysis, and I found that sort of the most interesting. It's the column 3, where you're looking at no MCL violations, but it's basically just using the level of contaminants in the water. So I assume you're trimming your analysis because of a linearity issue, but I wasn't entirely sure, so it would just be nice to know why you're cutting off some of these sort of really, really high contaminant areas, just to be a little bit more explicit about that. So the treatment definition, I think, as I read it, you use 1 day of contamination in a trimester to say that this is that this is a treated pregnancy, and I assume this is probably because you don't have daily information, but it wasn't exactly clear to me. Okay, I have 1 minute, so I'll be a little bit quick. So I'll skip that. I'm going to skip this as well because I'll give you these notes. The other thing I was really kind of curious about is whether or not you can extend this to look at sort of an RDD analysis of once you get over a contaminant level, like if you can kind of see places that are right below right below an MCL violation to right above. And I don't have a great, what do you call it? Research design, but thinking like health outcomes really shouldn't be affected by just being right on the other side or each side of these. But you might consider a public expenditures thing. Maybe there's crowding out of other public expenditures because they have to now invest in the water system. So anyway, that's all I have. Really enjoyed the paper. Thanks.
Great. So we've got about 5 minutes for questions. Richard, if you want to hop back up for those watching somewhere else. Do you want to hop back up to the podium?
Oh,
Yeah, so why don't you respond, and then we'll, if you have a question, please come up to the microphones. Or if you really want, I'll come to you. Hold on one sec. Let me give him a sec to respond.
Oh, I'll respond to that. Got it.
Yeah, I think all your comments are quite good. I agree with the more stringent definition of treatment for the MCL violations, and seeing if more overlap means more. The MCL violations, I mean, probably the thing that makes them most difficult to work with is that they're intervals, not points, so you don't actually know when there was contamination in the water. And you might think that public water systems respond to MCLs by lowering contamination, although there's a recent paper that says they don't in California, which is kind of unnerving. Regarding the what happens when a contaminant is not measured, well, that's also it's a thing I need to figure out. And basically, we use the contaminants that are measured in the contaminant group, which is not a very good approach, I don't think. So I agree with you. But something to think about. Thanks for your comments.
So we have a few more minutes for questions. Again, please introduce yourself before you ask your question.
Arlene Ash, University of Massachusetts Medical School. It is really cool data, and first of all, I love the whole replication technique. I think that it should be used by everybody all the time. But there's seems to me tons more that you could do with your data. As a mathematician, statistician, I would argue that you really shouldn't feel bound by saying this confidence interval lapped over the null effect, and therefore we can't say there's anything. It looked as if you had enormous consistency in terms of certainly the direction and sometimes the magnitude of the effect. The other thing is, it seems that there'd be a great deal to be gained using your more refined data to do something about levels of difference rather than just yes, no's in several places in your analyses.
So the confidence interval wrapping 0 in some of those cases, I was being sarcastic, but a little bit. But no, I agree with, it's pretty consistent with the previous study. It'd be nice, perhaps, but from a statistical point of view, I don't know how to do it, but maybe there's some meta-analysis approach I can take where together, because 2 studies, double the data, kind of, the centers should really be smaller, in some metaphysical sense.
Yeah, and I do think you ought to work harder talking with the people who are subject matter experts to come up with a more credible way to summarize total contamination. And there could be one thing you didn't mention, but maybe you've looked at, is the correlation in the occurrence of these various contaminants, and that could certainly explain some negative individual findings. I'm not sure, but it seems as if that's really a right place to look.
So I have a question, and this is going to come up in Dan and my work in a little bit. Do people ever know? Do people ever FOIA? Like, do you ever get some crazy anti-government person who wants to know, like, exactly all the readings they have about anything near them? Or are people totally oblivious to this unless there's a violation and such?
So my guess is that people don't know unless there's a violation, and this is because there is an organization, environmental working group, that did FOIA them and put them on their website, and then they stopped doing that in 2009, so I guess there wasn't enough demand for knowing the actual sample results. So that'd be my guess.
You should put that in the paper, because that's a point in your favor, that people don't, if people don't know about it because the only people who were asking about it stopped asking and stopped posting it, that makes the treatment much more exogenous. I also assume you can't taste the difference, but if that's true, you should put that in the paper also.
Mm-hmm. Actually, I don't know fully about that. I think Michelle would know more for her contaminants, but I don't.
Any other questions? Great, okay, thank you again. So our next speaker is Michelle Marcus from Brown.
Okay, great. Thanks everyone for being here today. I'm going to talk to you about petroleum pollution, regulation, and health. So as we'll hear about in just a little bit, this isn't working. No. Disasters like the Flint water crisis and the Love Canal tragedy have generated growing concern over human exposure to environmental pollution. And when we think about how governments can address this concern, they have several options, some of which include cleaning up pollution after the fact, regulating firms and industries to try and avoid future pollution, or simply informing the public and hopefully encouraging avoidance behaviors. While we know something about the health impacts of publicly funded large cleanups of sites like Superfund sites, we know much less about the ability of preventative regulations to mitigate health outcomes through requiring preventative technologies, and also we know much less about smaller, less publicized pollution sites. In fact, these small sites may be very numerous and potentially impact a very large population. In addition, because they can often be less publicized, they provide an interesting opportunity to study the role of information in inducing avoidance behaviors. So in this paper, I'm going to look at what is the health impact of a small but very common pollution source, and if in fact I find these sites harm health, how can we mitigate these health effects through either regulations or through providing information? The context I'm going to look at is that of leaking underground storage tanks and their impact on infant health outcomes. These tanks primarily store petroleum products. They're buried underground, and they were initially constructed of bare steel, which made them very likely to corrode and leak over time. In fact, as of the end of 2015, we've had over 500,000 confirmed leaks throughout the United States, and these have cost over $1 billion per year to remediate. Unlike some of the larger Superfund sites, these sites are characterized by more localized pollution, typically traveling distances less than 300 meters. In addition, they're less publicized, and their underground nature makes it much less likely that nearby residents even know of the existence of pollution when it happens. So this is useful for looking at avoidance behaviors. So this study relates to a number of different literatures, which I won't go into in detail. I'll just say that it's the first study that I know of to look at leaking underground storage tanks and their impact on health outcomes. This is the outline for my talk. I'm going to start with a little background. So this is like a stylized picture of what one of these sites might look like. And when we think about the mechanisms through which these health effects are likely to occur, we can think of 3 different channels. One is through groundwater contamination. So we see the gasoline plume can enter the groundwater table and travel certain distances. In fact, you only need a gallon of gasoline to contaminate 1 million gallons of drinking water. So even a small spill can be very harmful. Another channel we want to be concerned about is soil contamination. And thirdly, vapor intrusion, which is when vapors from these plumes can become trapped in confined underground spaces like basements or parking garages and become toxic to inhale. So we have these 3 contamination mechanisms in the back of our mind. In the US, we actually have quite a large reliance on groundwater. 39 million people are on small or very small water supply systems, which typically have fewer monitoring and notification devices. In addition, 14% of the population supplies their own water for domestic use, and this comes almost exclusively from fresh groundwater supplies. And in this context, a lot of the chemicals found in petroleum products can be harmful to health at levels that you wouldn't be able to detect either through taste or smell. The data for this study comes from 3 large states, Florida, New Jersey, Pennsylvania, for a period of 20 years. In these data, I have mothers' street addresses, so I'm able to precisely determine their residential location, as well as link siblings over time to do a sibling comparison. I have a number of health outcomes, which I summarize into 3 indices of overall health to make it a little bit easier to aggregate these related outcomes. And I have maternal controls that I include in my specifications. So with this vital statistics data, I'm able to link it to underground storage tank databases from these 3 states, which also have the precise geographic information, the tank address, and also leak timing information, which gives me the date of confirmed release and the date of case closure, which is when cleanup activities are considered to be complete. So with these two data sets, I'll first show you, I can't show you where people live, but I can show you the location of all of the leaking underground storage tanks in Pennsylvania and New Jersey. I have 113,000 facilities in the data and about 80,000 leaks. So about 60% of facilities experience a leak at some point. And this is the same for Florida. So you can see there's quite a few. And the nice thing about this is I have very precise geographic information, so I'm able to see exactly who's living near these leaking sites. And what I find is that it's more disadvantaged individuals are living near these sites. So here I have on the x-axis the distance to the nearest site, and I have a number of demographic outcomes, and across all of them you see near to the site is less likely to be white, more likely to be low educated, less likely to be married, more likely to be teen moms. And this is consistent with the broader environmental justice literature, which has shown this in many other contexts. For me, it presents an additional identification challenge, since any comparison of individuals living near the sites versus far the sites is going to be biased by these unobservable differences. So that leads me to talk a little bit about my empirical strategy. So obviously maternal residential location is not random, as I just showed you. So what I do in this analysis is I include maternal fixed effects and compare outcomes across siblings where one sibling is exposed in utero and another sibling is not. This allows me to control for all of those fixed characteristics about mothers. The remaining threat to identification is then whether there are any time-varying unobservable characteristics that may vary systematically with leaks. So to address this, I compare the relative difference in sibling outcomes between mothers within two narrow distance spans. Within 300 meters is my treatment group, and I use mothers 300 to 600 meters as a control group. These control mothers are used to account for any time-varying factors that may impact all mothers near the leak site. And these distances were chosen to be consistent with observed petroleum plume distances that they travel based on a survey of these sites. So I'll start with showing my specification here. The coefficient of interest is beta 1, which is the relative difference in sibling outcomes between exposed and unexposed siblings for mother near the site relative to that same sibling difference for mother slightly farther away. And I have a variety of maternal and child controls here, as well as mother fixed effects and year and month dummies. So I'll start with some visual evidence of what I find. So here I'm plotting that exposure coefficient based on 50 distance bins, and the outcome is an index of poor health, so larger values are worse health. And what we can see is when you get closer and closer to this leak site, there's more incidence of worse health outcomes, and these health effects seem to dissipate after about 2 to 250 meters, which is actually about the distance we would have expected given the survey of how far these plumes typically travel. So this is reassuring, because if we saw effects going much further distances, it may not be related to these leaks, in fact. So you might also be concerned that perhaps there's some time-varying maternal characteristics that may be driving this increase here. So we can look at the same figure, but looking at time-varying mother's characteristics, and we see this doesn't mimic the shape at all of the first graph we saw, so it's very unlikely that these are driving the results in the first figure. In a regression format, we can see the results here. The first three columns are my summary measures of overall health. They're all positive, indicating leaks are increasing worse health. The low birth rate and preterm birth are a little bit easier to interpret. And while I have days of exposure in the first panel, I just have a dummy variable indicating whether or not you're exposed in the second panel, so that's a little easier to interpret. So we'll look over here and see that leak exposure during gestation increases the probability of low birth weight by about 0.47 percentage points, which is about 7% from the mean. And we see a similar size effect for preterm birth as well. So I've tested lots of robustness for these results. I won't go into this here, but this main result's very robust to a number of different specifications. And in the second, after establishing that these sites do in fact harm health, the next part of the paper turns to see how these health effects can be mitigated either through regulations or information. And so I start with looking at regulations, and I ask the question, did tank technical standards reduce leak severity and protect health? So all existing tank owners were required to remove, replace, or upgrade their tanks by the end of 1998 to comply with spill, overfill, and corrosion protection. And these regulations were likely to reduce the size, duration, or distance that petroleum plumes would travel. So an infant in utero after these regulations were required is likely to have better outcomes. So what I do is I take data from Florida and Pennsylvania, which has installation and removal dates for tanks, and I am able to construct a facility-level date of compliance, which I show up here. It's the date of new tank installation as long as that installation occurred within 6 months of the last tank removal before the deadline for compliance. And unfortunately, I don't observe upgrades in my data, so for other facilities that had old tanks and are still open after the regulation, I just set the date of compliance to be the deadline. And you can see I'm just showing some pictures here. What I end up finding is that compliance with these standards ultimately eliminated the effect of leak exposure on low birth weight in particular, and so you can see low birth weight over here. And after, so the first vertical line is the earliest date at which old tanks may have been removed, and you see a pretty sharp drop in the poor health at that time. And the regression results confirm this visual evidence, but I won't go into this today. The final thing I do in this paper is I look at how do people respond to information about these leaks. This is a nice setting where people are unlikely to know of the existence of leaks, so we can study more explicitly how people respond when they do receive some information. So I look at two sources of information: direct notifications and local newspaper coverage. And I investigate how people respond to these sources of information in two ways. One is simply avoiding exposure. This would be like drinking bottled water, avoiding contact with soil and groundwater. And so I look here for reduced form evidence of this behavior. And I also look at whether or not individuals change their residential location when they receive some information. And what I find is that there is, in fact, a reduced form effect of information on health. I see that when individuals receive some information, their health is slightly improved. And I also see that there's moving response in terms of especially highly educated mothers are more likely to move when they receive some information. So this is an even more extreme form of avoidance. So to sum up what I do in this paper, I start by showing that even small localized pollution sites can harm human health. I find that leak exposure increases low birth weight by about 7% and about 7% for preterm birth as well. And also that these harmful effects of leaks can be mitigated both through information and regulation. However, these two channels have different distributional consequences. So for information, while it protects health, we also see this distributional shift of highly educated mothers moving away from these leak sites, which could actually exacerbate existing inequalities in environmental exposure to pollution. On the other hand, regulations are successful in protecting health and cost-effective. If we discount the stream of benefits over a 20-year tank life, in terms of low birth weight, these account for between 57 and 96% of the one-time fixed costs of facility upgrades. And unlike the information, these regulations disproportionately benefit low SES individuals who live nearest to these leak sites. So if we want to think of ways we can potentially mitigate some of this inequality and exposure, these type of regulations may be one step we can make in that direction. And that's it.
So Richard DeSalvo will be back up to discuss Michelle's paper.
So what I have to discuss mostly is not what she covered, it's the part of the paper that she didn't cover, but let me just talk about my take on the paper. So the first thing that I noticed is that there's 110,000 places in her data in these 3 states, roughly, with underground storage tanks, and almost 60% of them are at some point leaking. And I think we should step back for a moment and think about what that means, because these are all the gas stations, right? And 60% is a big number. So that's, I don't know, I feel like, I don't know, I think it's easy to like sort of just skim over that, but that means that one out of every 2 test stations I see are leaking. That seems like a huge number, and maybe I just don't understand what it means to leak. But anyway, she finds that low SES people living near these tanks are, I mean, usually that's the case, and it's usually in cities, which is really cool because a lot of this literature is exposure to natural resource extraction type things. So these things are actually in cities, not in the country, and so that's great. You have tons of data for all sorts of studies, and I think, anyway, and then there's this within mom fixed effect. There's an instrument. It's that full gestation instrument, but I'm not going to talk about that. And there's also donuts involved. But so her results are that the lusts cause these, these effects, which, as I said earlier, are quite in the middle of the literature of exposure, so it's quite reasonable impacts. And then there's policy moderation. The policy that basically says solve the problem seemed to work, and then there was another policy that she didn't mention in her presentation, which was sort of like watch the problem, which didn't actually work, which is kind of neat. And then the information provision is also a moderator. So I think very good paper. So I'm going to focus on a little bit on something because I'm sort of a public water system guy, I think, and a lot of in this literature anyway. Something she didn't talk about, which was she stratified by public water system versus non-public water system. And I was scratching my head thinking, is there a way that we can somehow get these standard errors down? Because if you look at the table, well, the coefficient on non-public water system is twice as big as the one on public water system. And then after I scratched my head for a couple days over this, I decided, let me just plot this. And then I plotted it, and I got this plot. And I realized that I have a deep misunderstanding of how much uncertainty there is in these estimates. So I have some ideas on maybe something that could be tried, but I kind of doubt that that there's any way to really crunch these standard errors down. I think we're going to end up saying that there's no real significant difference here. But so I was just thinking that, is there a strategy to extend public water system data to Florida? So in her study, she's got to restrict to Pennsylvania and New Jersey because those are the only states, basically those two states, and from what I know, Texas also have public water system shape files. So you can kind of just like, these are the places that have public water and these are the places that don't. But Florida doesn't have it, and a lot of other states that I work with don't have it, and it's kind of annoying that this data is missing. But what's interesting about her study is that really you just need sort of an indicator that's like you think this place has a public water system. And I think that it might be reasonable to try to predict public water system using density of population, basically, and at the census block level, and just impute in Florida and ask, here are the places that look like they should be public water systems. And in her study, I think it might work in her study, actually, because she really just needs to know that these places are cities, and these places are not cities, because a lot of the treated points are in cities, which kind of, it makes it different than most contexts. There's also this other approach, which there's this paper by Moilenbach, Spiller, and Timmons on gas wells. I think a lot of people are familiar with it. And it does the exact same ID strategy in that it has donuts involved. So basically, the donut is the control group, and then the treated group is near the point. So in Michelle's thing, it's lusts that are at the center, and then the distances are different. But the strategy is the same. And what MST does is they do this boundary sample restriction, where they take the boundaries, they take the boundaries of the public water systems and they restrict to the subsample. Now, I don't really believe the justification personally, but it's an American Economic Review paper, so certainly somebody did. But I mean, in the table, what you see is that when they do the restriction, they get stars, and when they don't do the restriction, they don't get stars. So it's certainly something that you can justify using this paper and try. I mean, maybe you've tried it, and in their data, it drops 70% of the observations. So certainly it does something. Probably just makes the standard errors bigger in your case. I don't know. Anyway, this is just a minor point about the definition of public water system intakes, but I think we can talk about this in private. But anyway, thank you.
Michelle, do you want to respond for a few minutes?
Yeah, these were really great comments. I'm aware of the public water intake well location, but yeah, we'll talk about that later. And this is a great approach. I have not tried that, so I will definitely give it a shot. We'll see what happens. And Florida, in terms of their public water supply systems, I pushed really hard to try to find them, and in the end, it was basically, you can try calling all of the public water supply systems and see if they have a a shapefile, but basically there's no aggregate collection of that information. Yeah.
Questions?
Dan Gross from West Virginia University. I was just curious, for the regulation data, after they change the regulation, there's still lots of leakages. Is that right?
Yes.
So what's the mechanism for the leakages not affecting people's health then?
Right. So I didn't have a lot of time to go into details, but the regulations had a number of different technologies that they required people to put on these tanks. So some of which were designed to stop leaks entirely, but a lot of them were designed just to contain the leak or catch it earlier. And so while so there's sort of this two-direction thing where we may have less leaks, but actually what I see in the data is there's still a lot of leaks, but they're just less severe, presumably because we're catching them earlier and they're contained without getting to individuals. So what I do in this paper is I look at individuals during a leak before and after the regulation goes into place.
So I have a question. I assume not all leaks are the same.
Right.
Meaning that like different parts of the tank are vulnerable in different ways, and if a different part leaks, there will be different flows and such. Is there any way to get data on what kind of leak, how much is leaking?
So I think that's good. That's a good point to bring up, and it speaks to something Richard mentioned as well. There are, 80,000 leaks in this data set. 60% of tanks are leaking, but not all leaks are the same. And what is recorded as a leak is any amount that leaks. So it could be very minimal or it could be very catastrophic. And so in, I don't remember if it was Pennsylvania, I think it was Pennsylvania, they did have some information on number of gallons leaked per incident. However, it was missing for the vast majority of cases, but using whatever limited data was there, the average was 524 gallons, which is enormous and makes me think that it's just selected, like the missing data is non-random for sure. So I don't put too much weight on that, and I can't use it in any analysis. There's just not enough information. The microphone.
I'm so loud that I usually. Paloma from CUNY. Do you know or do you have data on how long it takes to find that the leak is happening?
This is a great question. I glossed over this in this presentation for time, but so what I have in my data is the confirmed date of release. So unfortunately, it's likely that this is mismeasured relative to the true date that the leak started. So I've done a number of sensitivity analyses trying to see how, whether there are health effects that start prior to the official recorded start date of the leak. And I actually think that the timing I'm using currently is picking up the start of the health effects pretty well. And the reason I think that there aren't health effects prior to the official date is because it also takes some time for this pollution, the plumes to travel underground from the time it leaks to the time it shows up in an area that could impact humans.
But is it that there are authorities that are like supervising these in a seasonally or something like that, or in?
Oh, so anytime that they discover a leak, it has to be reported immediately.
So the gas stations basically
Yes,
notice
and
that
gas
it's happening.
station
Okay.
owners have an incentive to monitor how much product they're losing. So, and it's in the regulation that they have to report it. So there are fines if they don't. Great question.
Martin Anderson, UNC Greensboro. So you looked at tanks at gas stations. There are also a lot of residential oil storage tanks for, in New England, lots of people have oil heat. And various states over time have used programs and incentives to get homeowners to take out those tanks and replace them with other systems. Have you thought about doing the same type of analysis looking at these residential tanks? Because that would circumvent the problem of basically residential sorting and gas stations located in low-income areas.
Yeah, so actually, I am not separating to only gas stations here. There are a good number of residential tanks, although about 80% I would say are gas stations, at least based on like averages. Although I'm missing the smallest tanks. I think under 1,000 gallons might not be in these data because they're regulated in a different way. So looking at those tanks could be really interesting, and I could potentially separate them out from this analysis and look at them separately. So that's a good suggestion. Thank you.
Okay, let's thank Michelle again.
Thank you.
Our third presentation is Dan Grossman from West Virginia.
Okay. So this is joint work with David Slusky, who's sitting down here. And we're calling this the effect of an increase in lead in the water system on fertility, pregnancy, and birth outcomes, the case of Flint, Michigan. Okay. So quickly, we just want to acknowledge Michigan DHHS for providing us with data, West Virginia University CFE for material support, and Big 12 Faculty Fellowship for diverting football funds to some academics as well. So this is... Right. So this is city of Flint, Michigan, and in the foreground here you can see the Flint River. So the basic motivation for this paper is that Flint changed the source of their water in April 2014 from Lake Huron water, which was provided by the Detroit Sewer and Water Department, to water from the Flint River. So basically what happened is the Flint River was about 19 times more corrosive than the water that they were previously receiving from Lake Huron, and they were not treating this water correctly using anti-corrosive inhibitors, which meant that the new water source was basically leaching lead out of the pipes into local water system, into basically people's drinking water. Just very quickly, lead in the water is bad. There really is no safe level of lead in your water. The EPA allows a maximum contaminant level, but in all honesty, it's not safe to have lead in your water. And the other motivation for this is that lead issues are actually much more prevalent than most people realize. There's a number of cities which have lead problems involving either lead in the water, previous lead problems from pollution. And so we think that these, what we're doing here can inform, inform a lot of other cities as well. This is from the City of Flint website. This is just a corroded pipe. And so basically what happens is most pipes have corrosion in them, but if you have anti-corrosion inhibitors in your pipes, in your water, they would basically prevent most of this from leaching out into your water. Without that, this gunk inside could leach into your water and you end up drinking it. So the research question that we're asking is essentially, what is the effect of this water change in Flint on fertility and birth outcomes? We're going to be using geocoded natality data from Michigan from 2008 to 2015. It's the universe of births in Michigan over this time period. And we're going to be comparing Flint to areas around Flint that did not change their water source. And we're going to be estimating the causal effect of this water change on birth and fertility outcomes. So what I'm going to present today is going to be using difference in difference estimates. We've done this a few different ways. We've used synthetic controls. And then we're also going to try to do a couple analyses to try to get at whether or not this is a behavioral response or a biological response to this water. That kind of drives our results. This is the first study that we know of. I've talked to a few other people here, so maybe I should change the slide, to investigate fertility and health effects at birth for this Flint water change. We think it's one of the first studies to investigate sort of, use a natural experiment where they actually change the source of water on birth outcomes, and it also just documents health effects at birth of lead. Okay, so what we actually find is that fertility rates drop by about 10% following the water change in Flint compared to comparison areas. And fetal death rates actually increase in Flint after this water change, which is consistent with this being a biological response and not a behavioral response. Additionally, sex ratios skew towards more female births, This is all, in general, female fetuses are considered to be more robust. Male fetuses are more susceptible to fetal insults. So this is, again, evidence that this is a biological response and not just a behavioral response. Additionally, we find no evidence of behavioral changes, and we find some weaker evidence of worse birth outcomes as well. So how may lead affect fertility and birth outcomes? We're thinking about this in 3 different ways. First, is this a selective attrition story? Basically, this would be the culling of the weakest fetuses. So if this were to occur, it would clearly decrease the fertility rates, but its effect on health outcomes is a little bit ambiguous. If we're really just sort of cutting off the lower end of the birth distribution, it's possible that birth outcomes could actually improve, but it also could have a direct effect on infant health. This would be more of a scarring story. In this situation, you could expect the health distribution to shift towards more unhealthy births, and we can look at this, look for lower birth weight or reduced gestational age. And finally, we could also have an indirect health effect or a latent health effect that we will not be able to measure at the time of birth, but that may show up later in life. This is consistent with the Barker hypothesis that maybe these individuals might be more susceptible to cardiovascular disease later in life, but we won't be able to measure in this. Okay, very quick background on lead. Lead is actually an abortifacient. At the turn of the 20th century, pharmacists actually gave out lead pills to women who wanted to get rid of unwanted pregnancies. We know from Flint and from Washington, D.C. that lead in the water leads to higher rates of lead in the blood. And additionally, lead crosses the placenta, which provides a direct mechanism through which it may affect fetal health. From recent economics literature, we also know that higher rates of lead in young adult in youth is associated with criminality, with education outcomes, and with behavioral problems. Historically, we also know that lead is associated with higher homicide rates and fetal death. Okay, so the data is from Michigan Vital Statistics for 2008 to 2015. It's the universe of births in Michigan. We have this coded at the census tract level, so we can very easily identify Flint and other areas. We also have basic maternal and paternal demographic characteristics, and also characteristics of the child, of the baby at the time of birth. We're going to calculate the conception date as the birth date minus weeks of gestation, and we're going to assume that births are affected by the water change if they were conceived by November 2013. So the actual water change occurred in April 2014. This would mean that the births would be affected for about half of their gestational period. We can do this a couple of different ways, and the results are quite robust. Finally, we have a registry of fetal deaths in Michigan for the same time period. This is going to be all deaths, all fetal deaths that occur after 20 weeks of gestation and that occur in a hospital. So this is not the universe of fetal deaths, but it's the universe of fetal deaths that meet these 2 criteria. We're not going to be able to capture miscarriages with this data. Okay, we're calculating general fertility rate as the number of births per 1,000 women aged 15 to 49, and indexing this by county and month. And we're estimating a basic difference in difference here. On the left-hand side, we'll have general fertility rate, fetal death rates, and male-female sex ratios. And then water is going to be equal to 1 if the woman resided in Flint at the time of birth, and the birth was affected by at least, was affected by the water change. We're going to cluster our standard errors at either the city or the county level. Okay, so here we have some non-Flint births, columns 1 and 2, and Flint births in column 3 and 4. We can compare pre and post water change for each. These are just basic unadjusted difference in differences. We can see that general fertility rate drops by about 6 births per 1,000 in Flint. It doesn't change all that much in non-Flint areas. We see some actual evidence of healthier babies in the sense that abnormal conditions actually decrease in Flint, but we also see evidence of worse birth outcomes in the form of lower birth weight and reduced gestational age. And then finally, we see that male-female ratio is skewing towards more female births. All right, so these are our fertility rates. This is going to be a moving average to kind of get rid of some of the seasonality here. So the key takeaway here is that post-water change, the fertility rates drop precipitously. Okay, so we can see this in a regression form. Here, in the first 3 columns, we're going to compare Flint to the 29 most populous counties in Michigan. And then in the last 3 columns, we're comparing Flint. We're basically just collapsing those 29 counties into one observation. So we're going to lose a little bit of statistical power and we'll have fewer observations. But the key takeaway here is that this is a really, really consistent, really robust result. We find that fertility rates drop by 6.2 births per 1,000. And this is on a mean of 62. So this is really about a 10% decrease in fertility rates. We can look at some birth outcomes here. Basically, we see abnormal conditions consistently decrease, which is a positive birth outcome, but birth weight decreases as well, which is a negative birth outcome. In the interest of time, I'm going to skip ahead here. So the other thing we can look at is fetal deaths. So what we see here is that fetal deaths increase by 0.1 deaths per 1,000 women. This may seem like a sort of a small effect, but if we look at the mean is only 0.182 here, so this is about a 50 to 60% increase in fetal death rates for women in Flint following the water change. We lose a little bit of statistical significance in the last 3 columns, but the parameter estimates are quite large still. Next, right here, we're going to take fetal deaths, we're going to add them back to our fertility rates, and calculate basically a pregnancy rate in a way. So this is pretty similar to our main results. It's really still about a 6 births per 1,000 decrease in pregnancy rates. So what this means is that fetal death rates can really only explain about 3% of the decrease in fertility that we see. We can hypothesize here, but we cannot actually look at miscarriage data. We don't have any data on miscarriage data, but we think that it's very possible that miscarriages may be driving some of these results. And it's also possible that women are less likely to conceive during this time period. Again, we don't have data that we can actually look at this, unfortunately. So we do a lot of additional robustness checks, and I actually spoke a little bit faster than I was planning to, as I usually do. So I'll talk a little bit about these. We look at the sex ratios. They skew more female. As I mentioned, that's consistent with this being a biological response to higher rates of lead in the water. We look at the American Time Use Survey, and we look at intimate behavior. It's not a perfect measure of sexual behavior, but it's at least suggestive evidence that we see no change or even a slight increase in intimate behavior between Flint and surrounding areas. Again, I don't want to lean too heavily on that, but it moves in the direction that that there is no behavioral change. We can also look at all counties, not just the most populous counties. We can use big cities. We can also use different, we've looked at synthetic control methods for GFR. The results are really, really robust. We haven't been able to budge this at all. All right. I will skip ahead now, but just to let you know, we did a lot here, and there's a lot more that's in the paper that's not in this. But just to conclude, we find evidence of both selective attrition and scarring. Fertility rates decrease precipitously, fetal death rates increase, and sex ratios skew more female. This is all consistent with the selective attrition story. But we also find that the overall health of infants decreases, which is consistent with a scarring effect. To just give you a sort of a magnitude idea here, our estimates actually suggest that about 140 fewer births than expected occurred in Flint following the water change. Remember, our data goes through just 2015. And additionally, of the births that actually did occur, about 14 fewer births, about 14 fewer boys were born than we would have expected based on the male-female ratios prior to the water change. Behavioral responses do not appear to be driving these results. And we just want to point out that there's been a lot of discussion about cutting EPA funding for this basic testing for contaminants in the water. And based on our paper and Elaine and Richard's paper, we think that there's some serious health consequences that could occur if this funding is cut. All right, thank you.
Great, thank you, Dan. And Devalde from Bentley University is our discussant.
All right, morning everyone. Thank you, Dan and David, for organizing these great sessions on infant and child health. Dan and David always do great work. It's such a pleasure to read this paper, not an exception. So, of course, the research question is of first order importance, right? It's immediate relevance for policy because of recent cuts to the EPA and in compliance monitoring, but it's also important in terms of the scientific relevance of the question. We want to know what is the effects of lead exposure for moms and their kids. And so this is a medical question, and Dan and David are exactly capitalizing on how economists can contribute to this medical question, right? Through their identification strategy, getting closer to causal effects. And second, shedding lights on the mechanisms that could be underlying these effects. Is it biological? Is it compensatory behaviors? Is it environmental? Is it something else? The analyses are very transparent, very credible. I know a little bit of Dan and David's work, and as Dan's slide showed, just number of specification and robustness checks, everything I could potentially think of were already in there. It's a standard diff and diff approach with synthetic controlled diff and diffs as well that did not show up in the presentation. But they also do a really nice decomposition in terms of bounding how much of this is potentially a scarring effect versus a culling effect, which I really appreciated. And the results are very plausible. They find strong, consistent evidence of a reduction in the birth rate. Some of this can be explained by fetal deaths, but not all. And I actually believe that most of it is consistent with the miscarriage story. I don't personally think that the results from the ATIS on the intimate time use is the margin that would be affected. If you want to think about that, you might want to think about contraception use. I think that's the margin that would be affected. But overall, I think just the skewed sex ratio, the adverse effects on birth rate and some of the other birth outcomes, all of this is consistent with the biological adverse effect. So most of my comments are going to be mostly just extensions and sort of robustness checks or footnote type comments, and they're sort of all centered on this one big theme. Whenever we do analyses of this type, right, we pretty much often have to take sort of a reduced form intention to treat approach. Often out of necessity, and it's not that it's not an important thing. We want to know what is the net effect of this screw up on infant health. But because often we lack data on the first stage. We don't have data to estimate both the first stage and the second stage from the same data set. So most of my comments are sort of centered on how can we get maybe a little bit closer, targeted, zone in on where that effect is coming from and who is the most affected group here. So the really cool thing about the Flint water crisis is that it happened in such a nice, finite, discrete time interval. And I was wondering if we could sort of exploit the timing a little bit more, right? So as you mentioned, in April 2014, we had the switch in the water supply source from Lake Huron to the Flint River, right? And then we had August, September, E. coli, some of the bacterial contaminants were discovered in the water. And so we had all of these boil advisories. And people could actually taste the difference in the water as well, because this was harder water, and they could notice the taste. I know that came up in an earlier presentation. And then in October, we had the switch back to Lake Huron as the water supply, right? So if you actually look at some of the studies that have looked at the hospital clinical samples, right, the biggest increase in blood lead levels happened right in that stage, that first stage, right? There was about a 20 to 25% increase in blood lead levels. And then there was actually a decrease by about 10% right after the water advisors and all that. So this is where that compensation behaviors were sort of kicking in, right? And this is where I would find strong avoidance behavior. You had anecdotal evidence that there was shortages in bottled waters, and people actually sort of tasting differences in the water, they probably would be switching over to different sources, right? And then right after they switched back to the Lake Huron, everything went back to baseline very quickly. So, if you could actually, exploit this time a little bit better, where would we expect the strongest effects? I would think would be right in that first stage, right after that switch happened. And so in the paper, you guys are basically looking at conceptions that happened in October 2013 or later. And so if you think about, who is the group that's most affected here? So most of these women and their kids are going to be affected who are basically exposed in later trimesters, right? And there's some medical literature that suggests that it's really the first trimester that matters. So maybe if we want to sort of cut in on that window a little bit better, maybe look at conceptions that happened in January 2014 or later. So if you do that, oh, okay, all right. Everyone's going to be exposed to basically in the second and third trimesters, and some might be exposed in the first trimester. And if you can even zone it a little bit further, say April or May 2014 or later, then everyone here is going to be exposed in the first or second trimesters, and that's why I would find the strongest effects, right? And you may also even be able to sort of separate all of these effects in the same model by having it sort of an event study that decomposes the timing of the effects. I was also wondering if we could exploit spatial differences, right? So here's a map that basically tests the water tap levels in terms of how much of that is testing positive for 15 parts per billion. If you overlay this map with the lead pipes and the older residential structures were in Flint, it really correlates quite nicely. So there were certain wards, the inner parts of the city is really where most of the lead pipes were, most of the corrosion was happening, most of the exposure was going on. And I think maybe you have great data, maybe you can sort of bring out the spatial differences a little bit, right? And then the next thing is, okay, so even if I have two mothers who are being exposed to the same lead levels, the absorption rates will be very different between those two mothers. There's medical evidence that, the absorption of lead varies based on nutritional deficiency. Mothers who are more deficient in calcium, iron, zinc, vitamin C are going to actually have bigger lead exposures. And, mothers who have food insecurity, maybe BMI differences. So I was wondering if you could bring in data from the NHANES, right? So in the NHANES predict, which mothers are more likely to be deficient in these nutrients. Get the prediction, interact that with your treatment indicator in Flint, and that would be one way of getting in close to that late effect. These are the women I would think would be most likely to be affected. There'd be differences by STS education status and also by insurance status, because if these moms are going to the doctors would be advising them what they can do to bypass some of these effects, right? And my final slide, I'm not sure if that showed up in the presentation, or a little bit unclear in the paper. Is it possible for you just to compare Flint just to the rest of the county? Not use any of the other counties as control groups. The fertility data are a little bit noisy in where you say. I was wondering if you could clean that up a little bit. I think Michelle pointed out that there might be some migration effects going on. If you could check if there was migration, could these women just be living with a relative while this was going on? All of this is happening in May, October, September, maybe just show that the seasonal effects are not different between Flint and the control group, even in the prior baseline period. And of course, this water crisis is not happening in a vacuum, right? The reason this water crisis happened is because Flint is going through a financial crisis, so maybe just show that all of these things are not correlated with what the economic conditions were. WIC was expanded during this period to fight the crisis, so maybe put in some indicators for public insurance and public services to see that's not driving some of the results. You could also check outcomes for the mom, right? There are some outcomes for the mom in the vital statistics. The medical literature says that pregnancy, hypertension, and preeclampsia are other indicators that would be exposed to lead and more, and so you could actually use that as a robustness check. Compare your magnitudes to the rest of the literature. How did they line up? And I think, your study is really cool, right? Because, ultimately it's a cost-benefit analysis. It provides the inputs for that. So even if I use a very conservative VSL on the 140 sort of children who are not being born because of the crisis, right? That more than trumps, no pun intended, that more than sort of, is higher than any orders of magnitude to what the compliance cost might be, to what the monitoring cost might be, to what Flint was hoping to save by switching over from Lake Huron to Flint. But overall, really great study. These are just some small comments to sort of zone in the effects a little bit better. Really enjoyed the paper. Thank you.
Great, thank you, Deval. Dan, do you want to respond? Or? Yeah. I'm going to attempt to be co-author, taking notes and share at the same time. We'll see how it goes.
Thanks a lot, Deval. These are really great comments. I think that there's some things in here that we would really like to do. And one of the things that we've actually, while we've been doing notes, is we've been expanding the timeline. And I think that's really good. We've done some work on. We do have the GIS of the pipes, and we do have the ward data. We can, but we haven't really exploited that for our fertility results. Mostly just because the denominators get, it gets a lot noisier already, and it's already a little bit noisy in terms of fertility, just because, getting the denominator of women of that age group that live in these very specific areas. But it's definitely something we can look into some more.
Great, so we'll do a few questions for Dan and then more general questions. And please, again, come up to the mic and introduce yourself.
I have a question / suggestion, and is, do you guys have data on later outcomes? Because one of the ways women, unlike men, can flush toxins out of their bodies is through pregnancy and breastfeeding. So if you look at children later and children that are breastfed versus not, you could see differences, because the amount of toxins that you can flush out of your bodies through breastfeeding is incredible, like toxins from shampoos, soap, etc., and lead probably is even more. So that could be a good thing to look at later, if kids breastfed versus formula kids, or kids that were breastfed less, see if
Do you
there are
know,
differences.
I'm not that familiar with that, but do you know if the mothers are flushing it out, does that mean that it's going into the children then? Or,
Yeah, because,
Okay.
yeah. Basically,
okay,
so all
so
these
we
like,
don't have data on that, but, yeah, it's actually, but I mean, I guess that's a really interesting question then of, is that actually, or would those children actually be worse off? In
yeah,
that sense?
because I mean, they are born with lower weight, and
Right.
then you happen to be a good milk producer and you feed them, and then maybe you are worsening their outcomes
Right.
because you are flushing out all the lead from your body
Mm-hmm.
afterwards. So, yeah.
Yeah, I mean,
Yeah.
do we know, I know you're more on
Or
the
maybe it
medical
could be another
anecdote.
paper, a completely other paper.
Thank you,
yeah.
but also, I mean, there are all these physicians and pediatricians and anecdotal evidence. Have any of them talked about advising the mothers not to breastfeed?
I'm honestly not sure.
I
Something
haven't
we should
seen
look
that.
into, for sure. But yeah, that's a great question, and we'd love to get more data on children. We haven't quite figured out how to do it.
Okay.
But yeah, thanks.
Other questions for Dan? Yeah, please, if you come up to the mic.
Nice work. Did you separate by race?
We haven't separated it by race. We can. We just haven't actually.
Because city of Flint is very different from other counties or cities in the state of Michigan. So that might be interesting to see.
Yeah, that definitely would be interesting to look at specifically.
And I've done kind of the same study, and I found an increase in prenatal care among the Black African American mothers. So that, I don't know why, but I just got, so it might be interesting to see. But nice work.
Thank you. Yeah, no, we should do some robustness checks or some sub-analyses by race. It'd be very interesting to see. Thanks.
Other questions for Dan?
Hi, thanks. I'm Gabriel Facchini from the UI in Florence. So my question is kind of, well, a bit clumsy, but so one is like, because you didn't explain, like, why did they change? I guess it's just cost saving, and then, because that might explain something, or I don't know why they do it. And then this is kind of like a devil's advocate kind of question. So what if it's the other way around? What if the water in the lake is rising the level of fertility, and then you go back to normal when you change to the river?
Okay, so
That's kind of, it's a bit of push, but I don't know.
So the first question is a complicated one. So the city of Flint was basically under emergency management. So basically the choice to switch to the river water was made by a non-elected official. And it was a cost-saving measure. Basically, they expected to save somewhere in the realm of $12 million. So that's it's a complicated thing, and it's something that we actually have to do a little bit better job explaining in the paper. I didn't do it here just because I was short on time. And to your second question, I have to give that some more thought. I don't really know. I don't know why one set of water would be, help fertility, and I tend to think of it more as just potentially the lead in the water. It is well known that that lead affects fertility, so or fetal health.
Great, okay, thanks, Dan, again.
Thanks.
We have about 7 more minutes. If there's any other questions for the other speakers, any more general suggestions, any ways that leaky storage tanks could prevent lead, or any way that the papers might interact with each other. Okay, thank you all to everybody for coming, and thank you to our presenters and discussants, especially to Richard and Dan, who are doing double duty. And enjoy the rest of the conference, everybody. Thank you again.